À travers la tempête, elle nous guide.
First is the innermost tunica intima, made of an endothelium that minimizes friction as blood travels, and most also have a subendothelial layer made of loose connective tissue. Next is the tunica media, made of smooth muscle cells and elastic fibers. This muscle is regulated by the autonomic nervous system, which can initiate vasoconstriction, where the muscle contracts and the vessel narrows, or vasodilation, as the muscle relaxes and the vessel widens. This is important for regulating blood pressure and proper circulation. Lastly, there is the tunica externa, made of collagen fibers for protection and structural reinforcement. Within this layer, if looking at larger arteries and veins, there is the vasa vasorum, a system of much tinier vessels that supply the outer layers of blood vessels with nourishment. Now let's get more specific regarding the types of vessels. Arteries come in three groups. The first are elastic arteries. These are the largest and thickest, the ones near the heart. These contain more elastin than other vessels so that they can absorb more pressure, which is necessary as they have to withstand the pumping nearby. Next, there are muscular arteries. These deliver blood to specific organs, and these are the most abundant. And lastly, we have arterioles. These are the smallest, the ones that lead into the capillary beds. Moving on to capillaries, these are the smallest blood vessels, as we said. These have just a thin tunica intima, sometimes just one cell thick, often adorned with pericytes, which are cells that stabilize the capillary wall. The lumen of a capillary is very small, just small enough for red blood cells to fit through in single file. There are continuous capillaries, which are found in the skin and muscles, and these are the most common. There are fenestrated capillaries, which are covered with pores, allowing them to receive nutrients from digested food and to allow hormones to enter. And then there are sinusoid capillaries. These are found only in the liver, bone marrow, spleen, and adrenal medulla. Capillaries are always found in capillary beds. These are networks of vessels going from an arteriole to a venule. This typically consists of a vascular shunt, which is the central vessel, comprised of the medarteriole on one end and a thoroughfare channel on the other. And then between 10 and 100 true capillaries, connected to the vascular shunt by precapillary sphincters. When these are open, blood flows through the entire capillary bed, which is called microcirculation. And when closed, blood simply moves through the vascular shunt. This status will depend on what's going on in the body at any given time. Through the capillary beds, we have moved from arteries to veins, so let's mention some things about these. Where capillaries unite, they feed into a venule, and venules join to form veins. These look very similar to arteries, except that their walls are thinner and their lumens are larger, and there is less smooth muscle in the tunica media, while the tunica externa is thick, full of collagen fibers and elastic networks. Veins experience much lower blood pressure than arteries, and in order to prevent backwards flow, there are a number of venous valves that help direct blood flow, especially in the limbs where blood has to go against gravity to get back to the heart. With some of the finer details out of the way, we can safely zoom out and look at both the systemic circuit and pulmonary circuit as a whole and identify some of the key features of each. There are so many individual arteries and veins with specific names, far too many to name right now, but we can examine a few diagrams and perhaps one day you'll learn them all. First, looking at the pulmonary circuit, we see the oxygen-poor dark red blood gets pumped from the right ventricle into the pulmonary trunk, which becomes the pulmonary arteries. These quickly branch to form arterioles and then many pulmonary capillaries, where oxygen is gathered from the air sacs in the lungs. As it becomes oxygenated, the blood turns bright red, and these capillary beds drain into venules which join to form the two pulmonary veins that exit each lung. And these lead back to the left atrium of the heart to complete the circuit. From there, the systemic circuit begins, as the oxygenated blood is pumped out of the left ventricle through the aorta. This splits into many smaller arteries, which split into arterioles, and then capillaries that run through all of our organs. These vessels all have names that reflect either their specific location, the organs served, or the bone they follow, and they are not always symmetrical. The head and neck have specific arteries, as do the upper limbs, the lower limbs, and the abdomen. Then, of course, the blood makes its way through to the veins, the largest of which are the superior vena cava and the inferior vena cava. These feed back into the heart. And of course, there are, once again, specific veins found in the head and neck, the upper limbs, the lower limbs, and the abdomen, all with names that correlate with location, organ, or bone. Since most of us have no need to memorize all of these, we won't list them here, but medical students may want to study these a bit longer. So that gives us a decent picture of all the blood vessels in our bodies and the journey that blood takes as it supplies all of our tissue with oxygen and other substances. There is plenty more to discuss regarding blood pressure and other aspects of physiology, but for now, let's wrap things up with the circulatory system. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com. Professor Dave here. I want to tell you about the lymphatic system.
He knows a lot about the science stuff. Professor Dave explains.
After discussing blood, the heart, and all the various blood vessels, one might suspect that the entire circulatory system should be covered. But we would be missing a crucial component, and that's the lymphatic system. Let's take a quick look at this system now. We know that as the blood makes its way through the body, it enters capillary beds. And it is here that hydrostatic and colloid osmotic pressures force some of the fluid out of the blood to join the interstitial fluid. This allows for oxygen and various nutrients to be absorbed by nearby tissues.